Okay, let's take a look at surface area of revolution. Instead of rotating a region about a horizontal or vertical line, we'll be rotating just a curve about the line. We're not interested in the volume of the three-dimensional shape it generates. We're interested in the surface area. Volume would be what we'd have to pour into it to fill it up, while surface area would be what we'd have to, how much paint we'd have to use if we were to paint the outside. And so we take the curve y equals f of x from some a to b and rotate it about, in this case in our derivation we'll be deriving this version of the formula, rotating about the x-axis. And like what we do with the other formulas, we take the interval from a to b and chop it into subintervals. And we look at a typical, in this case it'll be a band, where we have the subinterval from some xi minus 1 to xi, and we have the point, so the subinterval is some band from here to here, xi minus 1 to xi, and we have these 2 points, the y values, yi minus, or f of xi minus 1 and f at xi, and we'll call that yi. This band is a part of the surface area. If we can figure out a formula for the area of that band, then we can add up a finite number of these guys and get an approximation to the area of the surface. And then to get more precise, we would just make the bands smaller. And so notice that the line that connects these 2 points here would represent the height. What we're going to do is unroll. We're going to like slice, think of this as like a label. We're going to slice it and unroll it, and what we'll have will be a rectangle. The height of the rectangle, and then the circumference. Once we unroll it, this will be the circumference. And so the circumference will be 2 pi r, and the height will be not this height off of the x-axis. That height off the x-axis actually represents the radius. Okay, and so the height of the rectangle would be this distance here. The length here that would be the distance between the points. Okay. And so what happens is, for the average we take an average. For the radius we take an average, and then for the length, what's going to happen is we're going to take this distance formula from connecting these 2 points. The distance between these 2 points would be like a piece of arc length. In fact, we'll use the same formula that we did for arc length. So we'll replace the length with the square root, and then we'll do sort of an averaging for the radius. And what's going to happen is, as long as delta x is small, then the we can replace the f at xi star with f of xi, and the yi can be replaced with f of xi star, and the yi minus 1 can also be replaced with f at xi star. So you have 2 of them here, divided by 2 that cancel. You just have f at xi star. We have the 2 pi, and this guy would be the radius, this guy would be the height. The length, the height of the rectangle. Okay, so the total, that's a 1 band, and we'll have a finite number of bands, n of them, so we'd add them up, and that'd be an approximation to the surface area. To get the total surface area to be exact, the best approximation would be to have a limit as the number of subintervals goes to infinity, the number of bands essentially goes to infinity. And this is our familiar Riemann sum, which leads us to integration. And so we integrate from a to b, 2 pi times f of x times this infinitesimally small piece of arc length. And that's the formula for arc length. Put it together with this, and we now have the formula for surface area. Okay. Now, it's the special situation where we're taking the curve y equals f of x, and we're rotating it about the x-axis. There'll be other versions of the formula, depending on which axis we're rotating about, and whether the curve is given to us as f of x or some g of y. Okay. And so let's look at the 4 different versions. We'll stick to having the axis either be the x-axis or the y-axis. We won't be removing away from the x or y-axis and using some other vertical or horizontal line. We'll stick to the x or y-axis. Okay, as long as the function is continuous, it has a continuous derivative, then if you're going to rotate about the y-axis, okay, just think of the distance off of the y-axis, then your radius is going to be x. So this would be your radius symbol, and then this would be your arc length, your length symbol in general. If the integration is in x, then this x will stay as an x, and then when it comes for the arc length part, the ds, then it's just our familiar part from arc length, 1 plus y prime squared underneath a root. That's if y is given as f of x, and we're rotating about the y-axis. Okay. But maybe it's to the point where we can't solve, maybe it's given to us as x as a function of y, and we want to do our integration in terms of y. If we want to do our integration in terms of y, this f of x can't, this x can't stay as an x. Right? Our integration is in y, and so we replace the x with the function g of y. That it'll be described to us as x is g of y, and we have to just put that function in its place. This will replace the x. When it comes time for the arc length part, since the integral is in dy, then actually the arc length, instead of saying y prime, we would be saying like x prime. We take the derivative with respect to y and square it and add 1 and take the square root. So if you're going about the y-axis, you just need to know whether your function is given to you as a function of y or as a function of x. If it's given to you as a function of x, the x stays as an x. If it's given to you as a function of y, then you need to replace the x with that g of y. Okay, and then we'll do the flip side where we have rotating about the x-axis. Okay, if you rotate about the x-axis, your radius is y. So this is the symbol for your radius. And then this is the symbol for your length. ds is the symbol for your length. And so if you're rotating about the x-axis and you have it as a function of x, then this y can't stay as a y. Okay, and so we'd have to replace it. That's what we did in our derivation. Replace the y with f of x. And then still have 1 plus y prime squared underneath a root. But if your integral is in y, then there's no reason to replace this y. You can leave it as a y. But then you'll be doing an integral in terms of y, and so technically then this will be an x prime that you need to square and add 1 to and take the square root. So it depends on what your axis is, and it depends on what your how your function is given to you. You pair those two up, you'll figure out which formula to use. How the function is given to you, and what axis you're rotating about. If it turns out that you can't work it one way, then maybe you can manipulate to solve the function for the other version of it and solve it that way. But let's work 3 examples. Okay, so first up, find the area of the surface formed by revolving the graph y equals x squared on the interval from 0 to root 2. We're going to rotate that about the y-axis. Parabola from 0 to root 2. We rotate about the y-axis, and so our radius would be x. The shape would look like that, and we're rotating about the y-axis, and we're giving it as a function of x. So the formula is going to be 2 pi x times the arc length formula part that we're used to. Okay. In general, the formula is 2 pi from a to b, in this case, x ds, and the x can stay as an x. Alright, so let's take the derivative. If f of x is x squared, then the derivative is 2x, and the formula would have us squaring that, 4x squared, and we'd have 1 plus 4x squared. Now, it's not just an arc length question, there is another part to it that's the difference with surface area. So we take and multiply that by x. We integrate from 0 to root 2. And this could be done with the u substitution. Whenever the degree in the inside is 1 more than the degree in the outside, that's an indication that you can do u substitution. Let u be the entire thing that's underneath the square root. Du would be 8x dx. Now you need to replace x dx, so you need to divide by 8. So your integral will become, keep the 2 pi, and then you'll have 1/8 of du replacing this x dx, and then you have the square root of u, or u to the half. Okay, the 1/8 du being here, and then you integrate u to the half, and you get u to the 3/2, but instead of dividing by 3/2, you multiply by 2/3, and then all together here, this 2 can turn the 8 into a 4, while this 2 can turn the 4 into a 2. So we're talking about pi over 6 times u to the 3/2, and then go back and replace what u was. U was 1 plus 4x squared. So this u substitution here on the side, it's kind of like side work. It helps us to find out that this antiderivative is pi over 6 times 1 plus 4x squared to the 3/2. Evaluate from 0 to root 2. So put a 2 in, a root 2 in, square the root 2, you get a 2. 4 times 2 is 8. 8 plus 1 is 9. So you have 9 to the 3/2 for the upper limit. You put a 0 in, you get 1 to the 3/2. And the pi over 6 is still on the outside. And so then 9 to the 3/2 is like 3 squared to the 3/2. And it allows us to be able to cancel the 2's. They'd be like 3 cubed, which is 27. 27 minus 1 is 26. We'd have 26 pi over 6, which can then be reduced to 13 pi over 3. That's the surface area when you revolve that curve about that x. Okay. Alright, let's work another example. Find the area of the surface formed by revolving the curve x equals 1/9 of y squared plus 2. About the interval where we're having y's between 2 and 6. We're going to rotate this time about the x-axis. Okay, so this is a parabola on its side. This isn't exactly where the y-axis is. This is at x equals 2. And so, I'm sorry, with y equals 2 and y equals 6, this picture is. But the y-axis actually is removed over here. The picture that the program that I use just puts the y-axis where the function starts at. It's kind of weird. Anyway, so we rotate this time about the x-axis. Okay, so the radius is going to be y. Now this formula, this function is given to us x as a function of y. And here's what the visual, of course, would be. This bowl shape with a hole in the bottom. And so we're rotating about the x-axis, and we're giving it as x as a function of y. We're going to integrate with respect to y. And so we integrate it with respect to y, then the radius is happy staying as a y. The formula would be 2 pi the integral of y ds, and so the y will stay there as a y. When it comes to ds, we actually have to do x prime, quantity squared. And so if x is equal to 1/9 of y squared plus 2, take the derivative and we get 2/9 of y. Square that and we get 4y squared over 81. Add 1. Here's where it gets a bit messy at. Here's what I recommend. I don't think we should leave it like this. I believe that we should, oh, I'm sorry. Hello? So what we're going to do different with this one is we're going to combine the 1 with the 4y squared over 81 and make the 1 81 over 81, so that we can combine them and call it 81 plus 4y squared over 81. We take the root of the top and the root of the bottom, and that comes out as a 9, the root of 81 on the bottom. And this is easy to deal with. If we left a fraction in there, I'm just gonna save that. It's gonna be too messy to deal with. And without the fraction, with this pulled out, we much rather deal with 81 plus 4y squared. Okay. So now we go to the integral, and we have 2 pi from 2 to 6, the y times this root. And now we just do the same kind of u substitution. Let u be the entire thing that's underneath the root. Du will be 8y squared, 8y dy. So 1/8 of du will take the place of y dy, and we'll be doing 1/8 u to the half du. But don't forget the 2 pi over 9 is on the outside. That'll be u to the 3/2 times 2/3. There's a lot going on here as far as canceling. So let's see. We have the 2 and this 2 canceling this to turn it into a 2. And we have 9 and 6 is 54. So pi over 54 times that original value of u, 81 plus 4y squared, to 3/2 power. And then we integrate that. We evaluate that. We found the antiderivative now. We just need to evaluate it at 2 and at 6. We plug a 6 in. 6 squared is 36. 36 times 4. And then we add on 81. And we get 225. Just leave it, although it is a perfect square, just leave it 225 to the 3/2. Put a 2 in. 2 squared is 4. 4 times 4 is 16. 81 and 16 is like 97 to the 3/2. So 225 to the 3/2 minus 97 to the 3/2. With the power over 54 on the outside, just leave it like that. Okay. So that was revolving around the x-axis, but having x as a function of y. So in both of our two examples, the variable that was part of the radius ended up staying as that variable. The first one was in x, and the second one was in y. So now let's look at a third version, where we have y is f of x. I'm going to go about the x-axis. This is the version that we derived. And so we're going about the x-axis, and y is given to us as f of x. Because we're going about the x-axis, we have 2 pi times the integral of y ds. But we're in x, so this can't stay as a y. We replace it with f of x. Okay, y is the radius when you're rotating about the x-axis, and ds is that length. Okay, so now we need to take the derivative. This is y prime. So if y is the root of x, its derivative is 1 over 2 roots of x. It'll be x and a half, and then you bring down a half, take it to the negative half. That would give us this guy. So when we square that, it's multiplying it by itself. If we have 1 over 2 root x, we multiply by 1 over 2 root x, it becomes 1 over 4 x. The x is also in the denominator. And so we need to add 1 to that. And just like in the last example, it's not going to benefit us to leave it like this. Let's make this into a single fraction by calling 1 4x over 4x and giving us 4x plus 1 all over 4x. So we can take the root of 4x plus 1 and the root of 4. Oh yeah, we don't have to do it this time. Because this is a root of x for the f of x, we can actually multiply these two roots together. Like basically bring this x into the root. And then we can accomplish our cancellation. make it one single root. The root of a times the root of b is the root of a times b. And so we could bring it in, cancel, and then we'd have the root of 4x plus 1 divided by the root of 4. And this is just a 2, and this 2 can cancel with this 2. So that we'll have just pi times the integral from 4 to 9 of the root of 4x plus 1. And that's just going to be u substitution. There's going to be an extra factor of a fourth. If you let u be 4x plus 1, then du is 4 dx. So to replace dx, you're going to have to take a fourth of du. And your integral becomes, keep the pi, and then you have a fourth of u to the half du, which is u to the, the 3 halves, times 2/3. And so these guys cancel. This becomes a 2. We have pi over 6 times that u to the 3 halves, but u is 4x plus 1. Put that back in. This is your antiderivative. All this side work was to help you figure out that the antiderivative over here is pi over 6 times that 4x plus 1 to the 3 halves. So we'll put a 9 in. 36 plus 1 is 37. Leave it like that, because it's 37 to the 3 halves. Put a 4 in. 16 plus 1 is 17 to the 3 halves. And so that's going to be it. 37 to the 3 halves minus 17 to the 3 halves. There's no combining these guys. And so that is your answer. Okay, so those are 3 examples of surface area revolution question. And we also derived the formula. Great.